All right, in this module, we're going to go over some common ceramic structures. So the first one I want to go over, because we talked a lot about sodium chloride in the bonding chapter, is I want to go over the sodium chloride or rock salt structure. And so the first thing I want to sort of bring your attention to when we talk about structures is that often the structures are named after the compound or mineral for which they were first discovered. And so even though this structure is named sodium chloride or rock salt, doesn't imply that it only belongs to sodium chloride. So when we talk about the rock salt structure, it can be sodium chloride, but it could also be potassium chloride or lithium fluoride or any of these compounds and more. It just refers to the arrangement of atoms, not what specifically is in it. Okay, so without that out of the way, let's kind of take a look at this. So this is one of those structures where we have a close packed arrangement of anions, and so you can see the Cl minus in the FCC arrangement, and then all of those octahedral sites are filled with sodiums. And I put the radii here, and then if we divide that, we see that that does fit with the cation to anion ratio for 6, which is the arrangement we have in this case. So the coordination number is 6 for both cases here. And this is just a snippet from that table that I showed you before, showing you that it's the cubic close packed, or FCC. The coordination numbers are both 6, and we have MX, which means 1 to 1. So 1 sodium for 1 chloride. All the octahedral sites are filled, and then these are some examples that you can see. So you can see sodium chloride, as you might expect, potassium chloride, but then also a lot of oxides. So a lot of what we call divalent, but 1-to-1 metal oxides. And these are mostly transition metals in these cases. So that kind of gives you a little bit of information about the rock salt structure. Let's now look at the cesium chloride structure, or CsCl. Again, same thing. It is named for cesium chloride, but other materials form into this structure. And if we do the cation to anion ratio here, we see that it's almost 1, right? So in this case, it's above the threshold, for octahedral. And so it actually prefers cubic, which is surrounded by 8. And so the reason this is the case, and the reason that you see over here that it looks like a cubic structure, so a simple cubic, right, of the anions, is because, again, it's those cations are much larger than in other structures. And so in this case, they're almost the same, right? They're very similar. And so instead of forming in that scheme that we saw with close pack structure, here it's a simple cubic arrangement of the anions, because they're so similar and because we want to try to maximize the number around a given cation. And so that's what's happening here. So this doesn't really fit with the scheme that we talked about because it has a simple cubic array. But the coordination numbers are both 8. So surrounding the cesium, you can see the 8. But also, if you think about the opposite, any one of these chlorine would also be surrounded by 8 in the center positions if you consider other unit cells. And so in this case, all the cubic sites, in this case, the cation is in that body-centered position. So this looks like BCC, but keep in mind it's not BCC either, because these two things are different radii. Even though it's slight, they're still a different radii, so we can't consider this BCC. So examples, these are all going to be relatively large cations. So you see cesium in the example for all of these with different anions. So that's another one of these common structures that we anticipate. All right, so let's kind of go over a modification to those density calculations that we did in the last section. So I showed you the same equation, but before we only had one type of atom or molecule. And so our density calculations didn't have to account for this summation, right? However, now If we take cesium chloride, for example, we are going to have to do that summation that we see because there is cesium, but then there's also chloride, right? And so we have to count up both species. And so this is just an example of that calculation for cesium chloride. So we know we have one cesium because it's in the body center position, and we count it whole because it's fully in the unit cell. And then chloride are in the simple cubic arrangements, but again, you're only counting 1/8. So again, that count of that is 1. And as a check, you should always kind of make sure that the 1-to-1 ratio here matches with your stoichiometry. So cesium chloride 1-to-1. So make sure it matches there. But this is an example of that calculation when you have multiple ions, but it could also be multiple atoms. So certain metals form alloys, right? And then we'd have to count different metals instead of ions here. So that's just an example of the calculation. Everything else is going to be similar in terms of how you operate these calculations. All right, the next structure we're going to talk about is what's known as zinc blend. So zinc blend is the name, the chemical name, or sorry, the mineral name for zinc sulfide. So it's still named after the kind of prototypical material. And again, this goes back to the stacking sequence that we saw, the anion packing being FCC, which you see here with the yellow sulfides, and then the tetrahedrals in this case occupied by the cation, in this case zinc. So, and they're half filled, and so that's what we see down here. So that gives us, if we kind of look at a cation, we can see that even the bond lines drawn, that those are the coordination. That's what it's surrounded by, the anions. And so the coordination is 4. And if we do that to a given anion as well, again, it might take a little bit more effort because we have to think about ions in another unit cell, but we can also prove that that is 4 as well. And so these are all tetrahedrally coordinated. That's the coordination number 4. And the materials that kind of go into these structures are zinc sulfide, beryllium oxide, and silicon carbide. And so we're going to kind of talk about what makes these similar, but keep in mind that the tetrahedral part, that's going to be key. Let's look at the next one. So this is called fluorite, and again, it's named for calcium fluorite, so named after the compound. But again, it can be a number of other examples. This one can actually be uranium oxide, thallium oxide, zirconium oxide, and cerium oxide. So a lot of metal oxides. And so the idea here is that, again, we kind of go back to a simple cubic array. So here, there's more atoms than is needed, but we have to build it larger because there's only so many of the cation, or sorry, of the interstitials filled. So that's why this unit cell looks bigger than it needs to. But in this case, the radius ratio is about 8.8, excuse me. So in this case, the cations are very large. And so if you look at all these things like uranium, cerium, these are all really heavy metals and really large metals. So in this case, the calcium in this case, or any of these, they're still quite small relative to the fluoride that we see. So simple cubic array of fluorides, but here the cubic, so the body center positions are filled, but you can see that only half of them are filled. So that's why we need to build this larger unit cell to describe the whole structure. And so in this case, those cations are going to have a coordination of 8, whereas the anions are only going to be coordinated by 4 because there's not that many. And another important thing to note here is the stoichiometry. So this is the, I believe the first one we've talked about where it's not 1-to-1. Here there's more oxygen. And so you can kind of visually see that there's quite a bit of the fluoride relative to calcium. So that fits with the stoichiometry. And again, like I said, a lot of heavy metal oxides kind of fall into this structure. So that's the fluorite structure. And with that in mind, let's also look at something called antifluorite. And so because it says anti, kind of think opposite on everything, right? So that was MX2 or MO2. This one's going to be M2O. So basically what we do is we flip the cations and anions. So basically I can take this drawing and I can label it such that in the antifluorite case, the smaller ones here are the cations and the larger ones are the anions, or I can flip it in the other case where the cations are larger that we had in the fluorite case than the anions. So this is basically just the flipped. And in this version, the anions do form a close packed array. So this is the FCC that you can, the FCC close packed structure of the white, which is the anion in our case. And then the cations are in the tetrahedral sites, but in this case, they're filling all of them because we see 1, 2, 3, 4, 5, 6, 7, 8. So that's all of them in this case. And so we have a coordination of, we have a ratio of M to X, which we've seen, and then the coordinations based on that are 4 for the metal. So if you kind of go through and look at any metal, any cation here, you see that it's coordinated by 4, and then the anion is coordinated by 8. And so again, you can kind of go through and look at this one they've actually drawn for you has the 4 over here and then the 4 over here. So it's coordination of 8. And things that fall into this are going to have that M to X, and they're going to be small cations that are usually monovalent, and then you have a divalent anion. And so you have lithium 2 oxygen, sodium 2 oxygen, calcium, so that the charge balances and we have more cations than anions. And I just want to make a kind of a note here. Even though it's kind of drawn like this with these very small, well, in this case, this very small calcium, most of these cations are quite large to the extent that they can sometimes actually be a little bit larger. So this drawing might be a little bit off scale for the fluorite. So I just wanted to kind of go back to that. As you can kind of see here, the ionic radius ratio is 0.8, which means that the cation is pretty close in size to the anion. So this kind of, I think, skews the drawing a little bit. So just so that you know that all of these cations are quite large. They may not be quite as large as oxygen, but they are still quite large. So this just skews it a little bit. But in this case, we flip it and we're looking at really small cations and rather large anions for the antifluorite structure. All right. So I also want to look at another common ceramic, and in this case, we're actually dealing with multiple cations. And so in this case, we have the perovskite structure, which is generically ABX3. So 2 different metal cations and then a single anion, which typically is oxygen. So we have the prototypical perovskite is barium titanate, which is BaTiO3, and this shows the structure of a perovskite. And so I'll put this on the quiz for this week, but what I want you to kind of do is see if you can come up with the A site coordination number, or nearest neighbors, and the B site coordination number for these two. So see if you can kind of visually detect that from this structure. Write that in the quiz, and then we will come back and discuss. Okay, so the A site in this case, if we look at it, so ABX3, if we compare that to this, that means our barium is the A site. And so let's look at barium. So barium is in these cubic arrangements, right? And so if we want to know the coordination for that, we're going to look at the anions. So that would be oxygens here. So if we let's look at this bottom, or no, let's look at this top forward barium 2+ here. And so it's going to be touching this atom, or sorry, this oxygen, this oxygen, this oxygen. So that's what we can see. But if you think about it, there's going to be an oxygen in each face-centered position, right? So in this plane up top, there's going to be 4 that it touches. Down here, there's also going to be 4. And then there's also going to be in the next plane over, there's also going to be 4. And so basically, you again, this is one where I would highly recommend that you draw out multiple unit cells with the same structure so that you can kind of verify the coordination number of 12 for the barium. The other one's a little easier to see. So if we look at the B site, which is titanium, listed second here, the B site is much smaller. It tends to have a higher valence. And here you can see that it's directly surrounded by the 6, right? The 6 oxygens that you can see. So that is a coordination number of 6. So I bring this up because this is obviously a more complex structure. We have multiple cations, but one thing I wanted to kind of draw your attention to is that the size difference. Barium's quite large, titanium's quite small, and so barium and oxygen are quite similar in size. And so if you put those two together, barium and oxygen, you see that it forms the FCC close packed array that we're talking about, right? The red plus the blue form FCC, right? If they're similar size. And then you have the interstitial, the body-centered position, filled with the titanium, which is the smaller. And so that's kind of what we see with this structure. So it's listed a little bit differently down here, but that's what we see in this case. And so examples of this, the perovskite structure, is actually quite an important structure for kind of advanced or electronic ceramics because it has some interesting electronic properties. And so we see this a lot in various sensors and so forth. But sodium tungstenate, calcium tin, yttrium aluminum, and a lot of other kind of titanates and various compounds. So most of these are oxides, and then there's going to be a difference, a pretty big difference in size between the two typically. So barium and titanium have big differences in size, and so that's the other key to this, and usually differences in charge as well.